Have you ever actually stopped to consider the really stark paradox of the mid-20th century? It's kind of wild to think about, but some of the absolute most foundational technologies of our modern world, I mean, we're talking the rockets that took us to the moon, the basic architecture of universal computing, even the synthetic materials we literally use every single day, they were all accelerated under one of history's darkest, most destructive regimes. Welcome to This Explainer. Today, we're unpacking the uncomfortable, but honestly undeniable scientific advancements of the Nazi regime during the 1930s and 40s. We're going to stick strictly to the data, the engineering, and the source material to figure out exactly how a massive drive for military dominance inadvertently drafted the technological blueprint of our modern era. So, let's dive right in. Okay, so here's our roadmap for today. We're going to systematically explore these vastly different domains, starting with the drive for autarky. Then we'll move into jets and ballistic missiles, lethal chemistry and synthetics, computing and automotive design, and finally wrap up with the post-war legacy.
First up, Section 1, the drive for autarky, engineering energy independence.
To really grasp the root of early 20th century German innovation, you have to look at a massive underlying geological problem. They were a rapidly industrializing nation, but they had practically zero domestic petroleum deposits. And, if you want to power a modern military and an industrial society, you absolutely need oil. But what they did have was a whole lot of coal. So scientists Friedrich Bergius, along with Franz Fischer and Hans Tropsch, stepped up and developed these complementary processes to literally synthesize petroleum from coal. The Bergius process used high-pressure hydrogenation to pump out high-quality aviation gas, while the Fischer-Tropsch synthesis used a cobalt catalyst to churn out diesel and lubricating oils. And guys, this wasn't just some small-scale lab experiment. It was the world's very first technologically successful synthetic fuel industry. Just to put that into perspective, between 1939 and 1945, these combined processes produced a staggering 21 million metric tons of synthetic fuel. It was basically an absolute lifeline for their entire industrial machine. Let's move right along to Section 2, jets and ballistic missiles, conquering the skies. So that exact same lack of conventional resources, paired with the desperate military need for speed, forced some pretty rapid advancements in aerospace. Consider the development timeline of the Messerschmitt Me 262, the world's very first operational jet-powered fighter aircraft. The design actually began way back in 1939 under the name Project 1065. But you'll notice a huge gap between its first piston engine flight in 1941 and its actual operational introduction in 1944. You might be wondering why the delay. Well, they ran into some massive metallurgy issues. They literally did not have the high melting point alloys required to withstand the crazy extreme temperatures of a jet engine. Plus, there was heavy political interference. High-ranking officials demanded it be redesigned from a defensive interceptor into a bomber, and that severely slowed everything down. But when it finally did fly with its Jumo 004 turbojet engines, oh man, it was vastly faster than any Allied fighter out there, using advanced aerodynamics like automatic leading-edge slats that massively improved its turning and low-speed performance. And that brings us to their massive pivot into rocketry. Let's break down the internal layout of the famous V-2 rocket, developed under Wernher von Braun. The primary engineering nightmare here? Heat. A rocket combustion chamber easily reaches up to 2,700 degrees Celsius, which is more than hot enough to literally melt the metal holding it together. So how on earth did they solve this? Well, if you analyze the engineering, they used what's called a regenerative cooling system. The fuel, which was a mix of 75% ethanol and 25% water, was actually pumped right along the double wall of the main combustion chamber before it was even ignited. This basically cooled the chamber walls down while simultaneously preheating the fuel for a much better burn. It's just a remarkably elegant thermodynamic solution, and it actually became the absolute standard for modern rocket design. Now, to really grasp the scale of what this engineering achieved, get this, 5,760 kilometers per hour. That was the maximum speed of the V-2. We are talking about the very first human-made object to ever travel faster than the speed of sound. This meant it could strike targets like London or Antwerp completely without warning, physically arriving before the sound of its own approach even reached the victims. There was literally zero defense against it. It was an absolutely unprecedented leap in ballistic technology, though we absolutely have to remember it came at a horrific human cost, relying heavily on concentration camp slave labor for its mass production. Transitioning now to Section 3, lethal chemistry and synthetics, molecules of war. While the engineers were busy conquering the skies, chemists were manipulating matter at the molecular level, ultimately creating some of the most complex and honestly deadly innovations of the entire era. Let's juxtapose these two chemical pathways for a second. On the one hand, we had the logistical miracle of synthetic fuels, which totally solved their petroleum crisis. But that exact same intense focus on chemistry branched off into a much, much darker path. Back in the 1930s, while they were researching organophosphate insecticides for agriculture, German chemists accidentally synthesized entirely new compounds. And these definitely weren't meant to fuel machines. They were specifically weaponized to fatally disrupt the mammalian nervous system.
Let's zoom in on the micro-level science here. When you examine the molecular structures of the G-series nerve agents, named that way for their German origin, by the way, it's chilling. The very first one, Tabun, was synthesized in 1936, and that was quickly followed by Sarin in 1939 and Somin in 1944. So how exactly do these things work? Well, these colorless and often tasteless organophosphates act by blocking a specific enzyme called acetylcholinesterase. That is the enzyme completely responsible for breaking down acetylcholine, which is a really crucial neurotransmitter. So without it, your nervous system basically just short circuits. It forces continuous muscle contraction, which super quickly leads to a loss of respiratory control and ultimately asphyxiation. They are so ridiculously potent that they can actually be absorbed right through your skin. To really grasp the macro impact of these molecules, just consider their modern classification. Today, United Nations Resolution 687 explicitly classifies Tabun, Sarin, and Somin as weapons of mass destruction. Interestingly enough, while the German military fully weaponized these agents during World War II, they actually never ended up deploying them on the battlefield, which is a huge historical fact that scholars still fiercely debate to this day. But regardless, their mere invention introduced a terrifyingly new reality to global warfare, eventually leading to total global bans and super strict stockpiling laws worldwide. Shifting gears over to Section 4, Computing and Automotive Design Civilian Foundations. Now, it wasn't strictly all just weapons of war. Some of the absolute most profound innovations from this time actually laid the direct, ground-level foundations for civilian technologies we totally take for granted today, like the computer and the compact car. Take early computing, for example. Between 1938 and 1941, an engineer in Berlin named Konrad Zuse built the Z3. Now, full disclosure, the Z3 had a pretty major limitation compared to what we use today. It completely lacked conditional branching. That means it couldn't do your basic if-then statements, but as modern research shows, the Z3 could theoretically still function as a universal computer, a Turing machine, by using a really clever workaround. By basically executing a single continuous program loop of arithmetic that simulated memory addresses and state updates, the Z3 could technically compute literally anything a bounded Turing machine could. Pretty wild, right? A deep dive into the source material highlights a really crucial detail. The Z3 didn't just compute with raw basic integers. Instead, all computations were performed with normalized floating point numbers, boasting a 16-bit precision mantissa. It read all its fixed sequences of operations straight from punch tape. What this means is that, despite its clunky electromechanical relay architecture, the raw mathematical logic Zuse employed basically laid a direct conceptual foundation for the exact architecture of the modern processors sitting in the devices we use every single day. Okay, let's see how this all builds into automotive design. The Volkswagen Type 1, which we all lovingly know as the Beetle, was famously commissioned back in the 1930s as the ultimate people's car for the shiny new Autobahn network. Now, Ferdinand Porsche is almost universally credited as the designer, but as it turns out, history is a lot more complex than that. As historical records point out, an Austro-Hungarian engineer named Bela Barini actually designed a conceptually identical vehicle way back in 1925. In fact, a 1953 court ruling officially affirmed Barini's authorship of the key concepts. We're talking the rear-mounted, air-cooled boxer engine, the specific transmission placement, and yes, even that iconic bug-like rounded shape. And he did all this almost a full decade before Porsche's prototypes even hit the drawing board. But regardless of its somewhat contested origins, the concept itself was undeniably brilliant. Just consider this number. 21.5 million. That is the total number of Volkswagen Beetles produced worldwide over an incredible 65-year lifespan. It somehow survived its incredibly dark origins as a propaganda tool for the Third Reich and completely transformed into a beloved global cultural icon, officially standing as the best-selling car of a single platform in all of automotive history. Finally, that brings us to Section 5, the post-war legacy, the diaspora of innovation. So what exactly happened to all of this extreme technological momentum when 1945 hit? Well, it definitely didn't just vanish into thin air.
The immense scientific output of the regime was systematically absorbed by the victorious Allies. Through massive secret initiatives like the American Operation Paperclip, some of the brightest minds and most advanced machines were transferred globally. For example, the Me-262's swept-wing and axial flow engine designs heavily influenced post-war aviation, directly shaping iconic jets like the American F-86 Sabre and the Soviet MiG-15. Even the whole synthetic fuel industry pivoted. Post-war plants in the British zone actually started temporarily using synthetic fatty acids to produce civilian everyday items like soaps and margarine. But arguably, the most profound transfer of all was in rocketry. Wernher von Braun and his entire V2 team surrendered, were fully assimilated into NASA, and ultimately went on to develop the massive Saturn launch vehicles that literally took humanity to the moon.
The sheer speed of the immediate pivot of this technology is honestly just astonishing. By 1946, captured V2 rockets were literally already being launched at the White Sands Proving Ground in New Mexico. Think about that. A devastating weapon originally designed to relentlessly bombard London and Antwerp was instantly repurposed as a scientific sounding rocket. These captured V2s reached mind-blowing record altitudes of 116 miles. They carried tiny payloads like fruit flies to safely test the effects of cosmic radiation, and most remarkably of all, they captured the very first photographs of Earth from space, high enough to clearly show the actual curvature of our planet for the very first time.
All of this leaves us with one final, deeply provocative thought. How do we even begin to reconcile the monumental leaps of modern science with the undeniably dark history of their origins? The fact remains that our modern ability to break the sound barrier, synthesize complex materials from coal, understand super intricate molecular biology, and even reach out into the cosmos, all relies on a blueprint that was forged in a crucible of war and immense human suffering. It's an incredibly uncomfortable reality of human history, for sure, but understanding the true origins of our technology is just absolutely essential to understanding the modern world we live in today. Thank you so much for joining me on this explainer, and remember to always keep questioning the history behind the science.